66 million years ago, the ultimate catastrophe. A massive asteroid slams into the Gulf of Mexico, blasting an enormous crater. The impact wipes out most of the world's known species, including the dinosaurs.
The asteroid impact is the only global instant catastrophe we know of. It happened in a day.
It caused such environmental disaster to our planet that 75% of all life went extinct.
But how did a local event trigger a worldwide cataclysm, killing dinosaurs everywhere? To find out, NOVA is following an extraordinary expedition to drill deep into the asteroid crater.
It's a really big effort on the human scale. People are just really excited about the science.
Science that will reveal new evidence about one of Earth's most devastating catastrophes. The day the dinosaurs died. Right now on NOVA.
Major funding for NOVA is provided by the following.
Check it out. Whoa. Horn 1, Horn 2, Horn 3.
In the Badlands of North Dakota, a giant skull, long hidden, is unearthed.
That's a lucky find to get the tip of the horn there.
It belongs to a Triceratops, the most famous horned dinosaur.
This skull is amazingly intact. You get the entire frill.
Paleontologists Tyler Leeson and Kirk Johnson suspect they've just uncovered one of the largest skulls ever found of this plant-eating dinosaur.
So here we're excavating a beautiful Triceratops skull. From the beak all the way to the back here, it's 6.5 feet long. You can see one of the brow horns right here. The other brow horn is sticking out right here. This is a piece that fell off. And then all the way back here, we have the big shield from here all the way over to here, which basically means the skull is about 4.5 to 5 feet wide. This thing would have been probably about 4 or 5 elephants in size. An absolute monster of a Triceratops.
Over 700 species of dinosaurs have been identified. For about 170 million years, these creatures ruled the Earth. Then suddenly, without warning, they vanished. To appreciate the extraordinary scale of this extinction, it's important to understand just how successful the dinosaurs were.
Dinosaurs are found in every habitat that we know of, from equatorial deserts to above the Arctic Circle. They were the dominant group of animals in the terrestrial realm all over the world.
So let's look over here.
If you're looking for clues about the dinosaurs' fate, there's no better place to search than North America. In New Mexico, Steve Brusati and Tom Williamson want to know how dinosaurs fared during the Cretaceous, an era lasting 79 million years.
That's bone? Yeah? Yeah? Okay.
Whoa.
Got a bone layer.
Check this out.
So this area here was a dinosaur paradise during the late Cretaceous period, so the final 10 million years or so of the time of dinosaurs. And so at this site right here, we have a lot of different bones.
It's a bone from the backbone of a horned dinosaur. This is probably Pentaceratops, which means 5-horned face, 2 brow horns, a nasal horn, and then a cheek horn on each side.
Pentaceratops, a plant eater, is a cousin of Triceratops.
Pentaceratops was the main plant eater on the landscape. These were the cows of the Cretaceous. They would have been everywhere. But there were other plant eaters too. It was incredibly diverse. Now, the things that were feeding on those plant eaters were some of the most famous dinosaurs of all, the Tyrannosaurs. So we have T-Rex here in New Mexico. During those 10 million years, this was essentially a jungle. It was dense vegetation, big trees. It's kind of like the Amazon today, maybe not quite that extreme, but the world was so much warmer in the Cretaceous, so this just promoted evolution. You had lots of species evolving, and so that was the world that these dinosaurs were living in.
But the long reign of the dinosaurs was about to end. Evidence can be found back in the Badlands of North Dakota, where Tyler Leeson and Kirk Johnson have almost finished excavating their skull. Triceratops were some of the last dinosaurs to roam the Earth. A clue to their fate lies in a rock formation called Hell Creek, deposited between 68 and 66 million years ago.
The Hell Creek rock formation preserves Earth's very last dinosaurs. So if you want to understand what killed the dinosaurs, you come to this particular rock unit to figure it out.
And there is one layer in particular that marks the bitter end. On a nearby butte, Kirk looks for it.
There it is. Right along here. This little thin clay layer doesn't look like much, but it represents the single worst day in Earth history.
It's called the KT boundary, and it's been found around the world.
So for the past 2 years, my team and I have been searching the rock layers right above and right below the KT boundary. And we found Triceratops, duckbill dinosaurs, T-Rex, Thescelosaur, any number of dinosaurs right below the KT boundary. But we have yet to find a single dinosaur fossil above the KT boundary.
What could have happened at the boundary to wipe out dinosaurs around the world? The first clue was found in 1980, when geologist Walter Alvarez and his father Louis, a physicist, tested clay from the boundary. The results stunned them. The layer contained a huge spike in iridium, an element that's rare in the Earth's crust, but common in space rocks.
And they realized this must have been one really big meteorite, an asteroid, that had hit all at once and spread iridium dust all around the planet. Once they thought of that, they said, wow, that means the giant asteroid happened right when the dinosaurs went extinct?
It was a radical idea. But how big would an asteroid have to be to end the reign of the dinosaurs? The Alvarez team calculated that the asteroid was almost 7 miles wide. Traveling at over 40,000 miles an hour, it exploded with the energy of billions of atomic bombs. As molten debris, fire, and smoke enveloped the planet, nearly 75% of all known species were wiped out. It was the first compelling theory for how the dinosaurs died. Given the force of the impact, where was a crater of the right age, type, and size? At first, nothing seemed to fit.
Well, everybody was looking for Alvarez's crater. Somebody had already found it, but no one paid attention to him.
Geologist Glenn Penfield had been searching for oil as he flew over the Gulf of Mexico. To find buried deposits, he was measuring changes in the Earth's gravity and magnetic fields, looking for aberrations.
On one of these flights, he came back and mapped the patterns he saw, and what he got was this amazing, giant circular anomaly, which he interpreted to be a giant buried crater.
But why are the rocks in the crater so magnetic? It's a question geologist Sonia Tiku has been studying.
When the impact took place, it introduced a lot of heat and a lot of shock pressures into the rocks that were there. This one got so hot that it completely melted. And here's a rock that simply broke apart from the force. Maybe it was a little farther away. So whenever these rocks melt and they cool down again, they form these magnetic minerals in the rock that can make them so magnetic that they can move a compass needle.
But the rock that broke apart doesn't move the needle at all.
So a great contributor to the discovery of this crater was the fact that you had this anomalously strong magnetic signal from these very strongly magnetized molten or formerly molten rocks.
In 1991, scientists finally determined that the crater was the right age and size for the asteroid impact. It was named Chicxulub, after a nearby town. But finding the crater only raised new questions. How did the impact unfold? And why did a local catastrophe trigger a global mass extinction, killing dinosaurs everywhere? To find answers, a team of scientists has come to ground zero. From a huge rig towering over the buried crater, they'll drill deep into the earth. Overseeing this multi-million-dollar operation is geophysicist Joanna Morgan.
Everybody wants to know, what killed the dinosaurs. This particular event led to our own evolution, so it's the most important event on Earth in the last 100 million years.
Here we go. Her co-leader is Sean Gulick, a marine geologist.
This is the ultimate test of some ideas. And they're not only my ideas, they're all the ideas of people who've been modeling how impacts work and modeling how the extinction happened. But without some samples from ground zero, we can't really test them.
And so we're investigating how this impact occurred and how it impacted life on the planet and how it led to such mass extinction.
On an earlier expedition, the team measured the buried crater to figure out the best place to drill.
We're looking for impact features. And so we basically take sound energy, we send it down into the subsurface, and it bounces off layers and comes back and makes us a picture.
The asteroid had punched a hole nearly 20 miles deep, gouging a crater 124 miles wide. Over 40,000 cubic miles of rock were displaced, rising into towering mountains.
So this is an absolutely amazing event. Mountains like the size of the Himalayas were formed in seconds.
As the mountains collapsed, they formed what's known as a peak ring, found only in the largest of supercraters. It's the only peak ring left on Earth. The next nearest is on the Moon. Until now, no one has ever drilled into a peak ring. So scientists don't know if it's made from rocks that came from deep in the Earth or nearer the surface. Finding out how far these rocks traveled is key to understanding just how violent the impact was.
We figured that this was the spot. We would have the best record of what happened at ground zero right after the impact.
To grasp the enormity of the Chicxulub blast, Sean visits Meteor Crater in Arizona.
This simple crater here was created by about a 150-foot asteroid impacting the Earth about 50,000 years ago. It's about a mile across. So while this looks like an enormous crater in human terms, it's actually of the smallest class because it's just a simple bowl. And we can see that there's been no rebound in the center of the crater.
Although there's no peak ring like Chicxulub's, the impact was still violent.
So it comes in at something like 26,000 miles per hour. It hits this spot, and it actually vaporizes and ejects most of the material that's inside the crater itself.
The intense heat of the fireball sent shock waves traveling over 12 miles from the blast. Gale force winds raged up to 24 miles away.
So it would have been a really dangerous thing locally, but certainly not a global event 50,000 years ago.
If this is what a 150-foot asteroid can do, imagine one over 7 miles across, with a crater 100 times wider. Back at the Chicxulub drill site, the team is working round the clock. To get to the buried crater, they must first drill through nearly 2,000 feet of limestone sediments. Only after crossing the KT boundary and broken melted impact rocks will they reach the mountains of the peak ring. An underwater camera shows the drill encased in a pipe as it bores through the seafloor. After reaching a certain depth, it's time to alter the drill and start collecting rock samples.
This is the drill bit. Each one of these little nodules is an industrial diamond. So as this drill bit spins, it basically cuts away a donut.
This kind of drilling is actually coring. So the teeth, or if you will, are on the sides of the bit, and there's a hole in the center. So as we're drilling down, we're literally collecting a column of rock. And as we go further down the borehole, we go further back in time until we actually get to the moment of the impact about 66 million years ago. And then beneath that, everything is in the crater.
The drill extracts cylinders of rock 10 feet at a time.
Okay, so this is the first full core of the expedition, we're excited to say.
This core contains limestone sediments laid down for millions of years after the impact. But how old are they?
What we're actually looking for is when we are in time. And how you're going to figure that out is by the organisms that lived in the rocks at the time, so the fossils.
To find these fossils, pieces of rock are ground up and analyzed.
So I'm looking at it in a microscope here. This is about 1,000 times magnification. And let's see what I see.
Paleobiologist Tim Braylow spots a species from the base of the ancient ocean's food chain called Discoaster. Because it appeared at a precise point in time and then quickly evolved into a new species, Tim can estimate the rock's age.
And they're telling us that this sample is probably about 54 million years old.
With each core, the scientists get closer to the moment of impact, when the peak ring was formed. But there's one thing they aren't likely to find: remnants of the asteroid itself.
And the reason is most of the asteroid is vaporized, and it rises up in an expanding vapor plume, and all that material gets ejected all around the globe.
After weeks of coring, Tim Braylower searches for fossils to see how much progress they've made.
Let me look at this in the microscope. I would say somewhere between 64.5 million years ago and 63.5.
Wow.
In just 10 feet, they've drilled back 10 million years.
We've been stuck in the same zone for a while, going forward very slowly, and then all of a sudden, boom, big jump in time.
This huge chronological leap means they will soon reach the KT boundary. On deck, everyone is on high alert. Sure enough, the next core has light layers and bands of dark ash.
Oh my God, well, this is Cretaceous.
Tim spots a fossil from the time of the dinosaurs.
Oh my God. This one lived right up to the boundary.
Next, they hit huge deposits of sandy sediments.
Just an ever-increasing pile of sand. And the fact it's completely structureless, just like you dumped it in place with the coarser stuff on the bottom and the finer stuff at the top. I think the only process on Earth that can do that's a tsunami.
Tsunamis are giant ocean waves created by a violent disturbance. When the energy of the impact punched a hole in the Earth, it pushed away vast amounts of rock and water, and tsunami waves rushed back to fill the void.
And the fact it's already like 12 meters thick probably already makes it one of the largest, maybe the largest tsunami deposit ever discovered. And if it keeps getting thicker as we go, it will absolutely, unquestionably, be the largest tsunami deposit ever discovered.
After the tsunami deposits, they find rocks melted and shattered by the impact.
I think this stuff's getting more chaotic as we go down.
At last, they're at the top of the crater.
Yeah, that has to be.
Beneath them lie the rocks in the peak ring, created in the first moments of impact. Then, out of nowhere, a roadblock.
I just got woken up because there's a problem with the drilling. So we're going to be down for a few hours. But in the meantime, I've heard that the core that did come up at this moment when we hit something different is pretty exciting.
As Sean examines the core, he sees signs of the peak ring.
Look at the color of the matrix. It goes from green to red.
It contains granite, a rock formed miles below the Earth's surface as magma cools.
We are now fully into impact rocks directly because it's granite, and so you can see these spotted, leopard-looking big chunks.
And some appear melted.
That looks like melt.
That does look like melt.
That looks like a giant cluster of melt.
It's not easy to melt granite, but the pressure of an asteroid impact could do it.
So, in effect, these were formed, the days that the dinos died.
More granite is recovered from the peak ring, but it's different. It's brittle, with crystals that are deformed or shocked.
And this granite looks nothing like any granite you've ever seen anywhere else around the world. So this impact has done something incredibly dramatic to these rocks.
But how did granite, buried deep in the Earth, rise for miles to form the mountains in the peak ring? It's a question that will be studied in the next phase of the project. After 8 weeks at sea, over 300 cores have been collected. It's time to wrap up the expedition and return to the lab.
I don't think it could have gone much better. We have very good core recovery, so we're pretty happy. I'll not forget this place quickly.
Once the cores are fully analyzed, the team hopes to understand exactly how the impact unfolded and turned into a global catastrophe. One of the biggest mysteries is why the Chicxulub blast wiped out dinosaurs around the world, especially in places like Patagonia, Chile, nearly 5,000 miles from the impact. At a site so remote, the only way to reach it is on horseback. Here, Marcelo Lepe has found dinosaur bones at the tip of South America.
This place is known as the Valley of Dinosaurs, one of the southernmost places with dinosaurs in the earth. It's literally a bone bed of 6 kilometers long, so it was full of life. Most of these bones comes from one special type of dinosaur, a plant eater. It's hadrosaurs, duck-billed dinosaurs.
Hadrosaurs were one of the most common dinosaurs to roam the planet. After conquering Europe, Asia, and North America, they headed all the way south. When they arrived here, this valley was a river delta. The changing climate and falling sea levels created a land bridge, letting hadrosaurs even reach Antarctica.
The changing conditions were not a problem for the group of hadrosaurs. They conquered a lot of environments. They moved around the world.
Not only did dinosaurs conquer every corner of the Earth, they grew to extraordinary sizes. One of the biggest ever found also lived in Patagonia. This titanosaur weighed over 70 tons and was longer than 3 city buses. So how did the asteroid blast seal the fate of dinosaurs thriving far from Chicxulub? It's a question scientists hope to answer in Bremen, Germany, where the columns of rock, one after another, have been laid out on the floor. Unraveling the secrets of the impact and its aftermath is a colossal task. Nearly half a mile of rock must be split, tested, and photographed. As the cores are studied in chronological order, the story of the catastrophe becomes clearer. This core, from above the crater, is what the seabed normally looks like. Layers of similar-looking rock laid down very slowly. These 10 feet of limestone took about 10 million years to accumulate. But after the asteroid struck, geology moved at hyperspeed. The next 2,000 feet of rock were deposited in a single day as the asteroid blasted deep into the Earth's crust, leaving a chaotic jumble of rock.
So what we have here are granites, like you would have in your countertop in your kitchen. Only these granites are from the Chicxulub impact crater, and they have really been through the ringer. They're distressed granites.
So what caused the granite to rise upward for miles to form the peak ring?
So I have an example of what normal granite would look like. You can see how hard it is, and that you could slab this and make a countertop out of it. It's remarkably solid stuff. But this, on the other hand, is changed completely by the pressure waves moving through it, by the shock of the impact. It's super light, and it's actually breakable because it's been so distressed, so damaged.
This shocked granite acted like a liquid. It flowed upward like the darkened, melted rock above it to create the peak ring.
And so the asteroid hits and it opens up a big hole, and like everything acting like a liquid, it then splashes up and collapses outwards, and the ring of mountains is then made from rocks taken very deep and brought to the surface.
Finally, after millions of years, the first violent minutes of impact, and the peak ring's formation is exposed. The core above, full of shattered rocks, tells the story of the tsunami that followed.
This one is so unique. It's one that has mixed things that would never normally be anywhere near each other. Just pretty amazing. So if you look at the pieces of rocks, you see both ones with angles, corners on them, and ones that are quite rounded. Now, something that's rounded has seen water.
As the impact shattered the Earth's crust and pushed away the ocean, tsunami waves rushing back in knocked off the corners of rocks and mixed them up.
We have a big hole made, the ocean has been pushed away, the ocean's got to come back. And it's so hot that it probably turns right back to steam, and we have this mixture of some rounded stuff and lots of broken stuff together to create this interesting-looking rock made by an impact.
But what did all this mean for the dinosaurs? To find out, the scientists must figure out the exact size of the blast. And for that, they'll look at the most powerful explosions we humans have made. This is the Nevada test site, where nearly 900 nuclear bombs were detonated. To understand the effects of a nuclear blast, the military built a village here named Doomtown.
Yeah, I can see the direction from which the blast came.
Mark Boslow and David Dearborn studied these explosions.
Tests like this are really important. Those of us who work on asteroid impacts, we naturally started comparing them to nuclear explosions, to similar phenomenon.
Most of the damage is done by the fireball and the heat that is generated, or the blast wave as it goes by.
The intensity of a nuclear explosion can be measured by the way it deforms a common crystal found in the Earth, creating something called shocked quartz.
The pressure is so high in a shock wave from a nuclear explosion that it actually exceeds the strength of a crystal. So it squeezes the crystal. When the crystal is squeezed, it has to fragment, it has to distort, and that's what shocked quartz is.
Quartz was found at Chicxulub. So how much did the asteroid blast shock it? Back in Germany, Joanna Morgan is trying to find out.
So this is a microscope image of a piece of shock quartz that we recently drilled from the Chicxulub impact crater. There's lots of lines here. Essentially, the more lines we have on the screen, different directions, the more shocked this rock has been.
Since it's known how much pressure it takes to shock quartz, Joanna can figure out the energy released by the impact.
This event was equivalent to about 10 billion Hiroshimas. Absolutely enormous. I mean, the biggest event in the last 100 million years, the most, catastrophic thing that happened to the Earth.
Using clues from the cores and computer models, the team can now accurately reconstruct the Chicxulub impact. It begins with a massive asteroid, 7.5 miles wide, heading towards Earth at over 40,000 miles per hour. Upon impact, it punches a hole nearly 20 miles deep in the Earth, shocking and melting granite. The rocks flow like liquid, rising over 18 miles before falling to form the mountains of the peak ring. Heat from the fireball reaches 10,000 degrees Fahrenheit. It creates a shock wave, which travels faster than the speed of sound, generating hurricane-force winds. Within 600 miles of the impact, everything is decimated. So what happened to the dinosaurs living in New Mexico?
Standing out here is really hard for me to imagine what it would have been like on that day 66 million years ago when everything changed. So when that day started, this whole area here would have been teeming with dinosaurs. And then, about 1,200 miles in this direction to the southeast, the asteroid hit. And very quickly, the dinosaurs would have realized that something was wrong, because there would have been an enormous red glowing cloud that would have filled up much of the sky here. That wouldn't have really affected the dinosaurs very much. They would have seen it, but it wouldn't have hurt them. Now, their cousins down in Texas, about 1,000 kilometers closer to the impact site, they were toast. They were incinerated. They were vaporized.
Around the world, most dinosaurs were still alive. But the clock was ticking. A deadly, unstoppable chain reaction had been set in motion. And there's one core from the crater which reveals how the Chicxulub impact became a worldwide disaster. It's full of dust, melted rocks, and debris from the impact.
So we are now at the top of the boundary layer. So this is sort of the end, if you will, of the tsunami deposition. And then we end up in a sort of a dark band here. And what we think these are is the initial falling out of the sky, basically, of the larger particles. Probably things that came out of the vapor plume, made a trip all the way around the world before raining back down into the crater.
When the asteroid vaporized, it produced this huge plume of rock vapor that expanded upward at very high velocities and outward over the planet. And as it went up, it cooled and formed tiny little spheres about the size of a grain of sand. Now, when these things re-entered the atmosphere, they got hot again from the friction of the air, just like shooting stars. But if you were standing on the ground and looking up, there was an incredible number of shooting stars, so much they didn't look like individual stars. They looked like a sheet of red-hot lava far above you, glowing from all directions. And the glowing hot lava was emitting an amount of energy that's a few times larger than the sun.
In New Mexico, dinosaurs may have escaped the initial blast, but that rain of molten debris would prove even more deadly. Computer models show that just 11 minutes after impact, the skies began to darken.
It wasn't really a case of fire and brimstone raining down from the heavens. It was more a case of all of that stuff heating up the atmosphere and turn the atmosphere into a giant radiator.
For several excruciating minutes, the sky radiated searing heat.
On the ground here, it would have been as hot as a pizza oven. And so that would have destroyed a lot of the dinosaurs, but it also would have started wildfires.
Temperatures soared and smoke filled the skies. Soot and charcoal found in KT boundaries suggest that much of the world burned.
The fire was started everywhere, which causes what's called a mass fire. The mass fires can be much hotter than a normal fire. All the leaves on the ground caught fire, the leaves on the trees caught fire, the underbrush caught fire. There's winds at hurricane speeds rushing into the fire, drawn upward into the rising flames, and they consume everything. And this vapor quickly spread across the planet. It probably only took a few hours for it to reach the farthest reaches of the Earth.
The disaster was now truly global. Even creatures in the sea couldn't escape. Oceans don't usually burn, but they can turn deadly. Clues to how the ancient ocean changed can be found behind a shopping mall in New Jersey, in an abandoned quarry. Here, paleontologist Ken Lacavera has been working at a fossil site that offers a glimpse of life in the oceans before the impact.
As we go down this road, we go millions of years back in time. When we're down at the bottom of the quarry here, we're right at 66 million years ago.
Back then, when dinosaurs ruled, the world was warmer and sea levels much higher.
So this is all underwater at the time. If you look up over at the tops of those tallest trees, about 75 feet above us, that's about the level of the ocean 66 million years ago.
At the bottom of the quarry, Lacavera has found fossils of ancient sea creatures that thrived during the reign of the dinosaurs.
We find the remains of mosasaurs here. Mosasaurs are giant marine lizards as long as a bus. They have paddles for limbs, they have a 6-foot jaw, and with these really ferocious teeth. And it would fit into its mouth here along with scores of other teeth. This thing is a sea monster.
Scientists have excavated over 25,000 fossils at this site. On display in a nearby warehouse, they provide a snapshot of how the ocean changed.
What it shows us is how a marine ecosystem can collapse during a mass extinction event. And you see the last mosasaurs die out, and they're replaced by crocodiles and sea turtles, because the smaller predators take over once the big apex predator, the mosasaur, dies off. And on the sea bottom, the food chain is collapsed, and what you have is a dwarfing of organisms that are starving.
Fires had devastated the land, but what caused the ocean ecosystem to collapse? The answer may come from something missing in the cores. A mineral known to be abundant in Yucatan rocks, gypsum.
This is gypsum. This was part of Yucatan at the time of impact. If we look at the core that we've recovered from the Chicxulub crater, we do not find any gypsum. It's all gone. It's supposed to be full of it, but it's not, which means that almost the entire sequence of gypsum that was present at the time of impact went into the atmosphere.
Gypsum contains sulfur. When these particles reach the upper atmosphere, they block the sun and cool the Earth.
And you see this in volcanic eruptions. So when there's a major volcanic eruption, the next year, frequently there's a year without the summer because the sulfur aerosols are still up in the atmosphere, reflecting sunlight back into outer space. When it finally rains out, it's going to create sulfuric acid.
This devastated coastal waters, lakes, and rivers as they turned acidic. But the darkness that preceded this rain of acid dealt a far more lethal blow.
This material, vaporized by the impact and released into the atmosphere, is the killer.
The dust, sulfur, and soot blocked out the sun. Photosynthesis stopped on land and in the sea as darkness prevailed.
It was probably less than the light that you get on a moonless night. Because there's no light reaching the ground, it would have also gotten very cold. And within a few days, the temperatures would have dropped below freezing.
To find out what happened to plants, Kirk Johnson searches for ancient fossilized leaves in the Dakota Badlands.
We find leaves both above and below the KT boundary, but they're different leaves. About 60% of the species of Cretaceous plants disappear at the KT boundary. So So there was not only a dinosaur extinction, but there was a major plant extinction as well.
The world turns gray. With little to eat, dinosaurs, mosasaurs, and nearly 75% of known species go extinct. What the asteroid set in motion, rapid global climate change, ends. The age of dinosaurs is finally over. So how long does it take for life to recover? To find out, Sonia Tiku is studying something that at first seems to have little to do with life at all. The magnetism of rocks from the crater.
The Earth is essentially a big bar magnet. It has a north magnetic pole and a south magnetic pole. And whenever rocks form, they actually record the direction of the magnetic field at the location that they formed at. So that magnetism is preserved in rocks as a direction.
That direction changes every few 100,000 years when the north and south magnetic poles mysteriously flip. After the asteroid blast, as the crater's melted rocks cooled and hardened, they recorded the Earth's magnetic polarity at the time of impact.
And that direction shows up throughout the crater. However, there are a few exceptions where in some of the rocks that have melted, there are directions present that are the exact opposite of what the Earth's magnetic field was at the time of the impact.
It was a puzzling discovery. The impact was over. So why were these rocks remagnetized when the Earth's magnetic poles flipped some 300,000 years later?
There's only one thing that can last for 300,000 years after an impact to remagnetize these rocks, and that is chemical reactions.
Reactions caused as scalding water formed new minerals in cracked rocks, like the red crystals found in this core.
So the chemical reactions that are required to create new magnetic minerals have to take place at temperatures that are at least 200 degrees Fahrenheit. That's pretty hot.
And it means that for 300,000 years, much of the buried crater was a smoldering dead zone. Only heat-loving microbes could survive. But above the crater, sediments accumulating on the sea floor tell a different story. Fossils collected by the expedition show that tiny plankton returned within 30,000 years of the impact.
And one of the first species that we observed was Bratosphera. And this species is really cool because while everyone else is cleared out and can't live in these horrible post-impact stressful environments, Bratosphera is like, it's the end of the world as we know it, and I feel just fine.
Whatever survived was now set to inherit an Earth once ruled by the dinosaurs. But is that really the end of the story? Could some of the dinosaurs' descendants still be among us?
Whenever you look at a big extinction event, it's not important to look at what went extinct. It's important to look at what survived.
Scientists now believe that modern birds are living dinosaurs. Specifically, an avian group that evolved from two-legged dinosaurs called theropods.
Avian dinosaurs go through the boundary. They're the ancestors of the diversity of living birds that we have today, which is at least 15,000 to 18,000 species. So I think you can make a pretty good argument that we're still living in the age of dinosaurs.
As for our mammal ancestors, how did they avoid extinction?
On the tip of my finger right here is a lower tooth of something called Mesodma. There's a little guy who's probably about the size of a mouse. This is one tough little mammal known to survive through the global devastation. It's a blade-like tooth. It was able to feed on things like insects and seeds, so it didn't have to rely on photosynthesis.
Mammals, which had been small-bodied things, rarely larger than raccoons, suddenly found themselves without any competition. And those animals rapidly evolved. And within 10 million years of the extinction of the dinosaurs, there were mammals that were as large as some dinosaurs.
Without the mammals surviving through the extinction, we wouldn't be here, because one of those groups of survivors was our own ancestors. They're among those very few mammals to survive through that extinction event.
But chance also helped us. If the asteroid had hit just a few seconds earlier or later, it might have been a very different story. A story that might never have included any of us.
Where it hit was particularly disastrous for life. Lots of this volatile material got kicked up into the atmosphere. And if it had just been slightly different timing relative to the rotation of the Earth, it could have hit the Atlantic Ocean or the Pacific Ocean. And if it hit one of those instead of Mexico in between, that event might not have been significant enough to actually have ended the age of the dinosaurs. And in fact, possibly we might not have grown to take over the planet.
Modern humans have only been around for about 300,000 years. The question is, can we last even a fraction of the multi-million-year reign of the dinosaurs?